In this module, we are starting another bonding theory. So this one is called molecular orbital theory, and it's abbreviated MOT. In molecular orbital theory, what we do is mix together atomic orbitals, or we'll abbreviate these AOs, on adjacent atoms to create molecular orbitals, or MOs. And the thing that we are doing, this method, is called LCAO, which just means a linear combination of atomic orbitals. And the result, the kind of like weird result out of all of this, is that bonding electrons can be delocalized over an entire molecule in some cases. So delocalized means they may not be perfectly confined between two nuclei in the sort of two electron shared bond that we've talked about for everything until this point. Um, and so you're probably wondering, oh my God, why? Well, valence bond theory can't answer everything. Um, it works really great. I mean, it works well enough that you will use it in the future, right? Like Lewis theory and Lewis bonding theory and the pictures that we drew, still not perfect, but we still use them constantly because each different theory or application will be the sort of like good enough for the thing that you need to look at. So for molecular orbital theory, right, it's great, but we need computers to do a lot of these calculations for us and even to think about bigger molecules or especially anything not symmetric later on. So we're going to do really small molecules in MO theory compared to what we did in valence bond theory, but you will still be able to construct this theory of bonding and apply it to some molecules. So I have some examples of some things that valence bond theory can't answer. So it fails to predict certain properties of molecules. Um, Oxygen is paramagnetic, which means that it has unpaired electrons. Now, if you were to put together a Lewis model picture, right, draw a Lewis structure for O2, it would look like this Lewis structure that I have here. Everything is paired up. If you drew a valence bond theory picture for this, there's no place where electrons would be unpaired. However, experimentally, we know oxygen has unpaired electrons. Um, on the fun, cool side of that, the way that you test that or show it or figure it out is by making liquid oxygen, which is also pretty because it can be kind of bluish in color. And if you pour it between the poles of a magnet, it will be attracted to one side of the magnet because of the unpaired electrons. The other example is that experimentally, the carbon hydrogen bonds in CH4 are not identical, which we we just in a very recent video drew a valence bond theory picture of CH4 where all four of the bonds looked identical. And that was the best that we could do based on that theory. Now, you will actually not draw an MO diagram for CH4 because it's too complicated for what we're going to do by hand. But MO theory will show how CH4 bonds aren't, all four of them are not perfectly identical. So the way that we do this is that we look at adjacent atoms. So we're only going to do diatomics, and you will mix or add together orbitals of the same type from each. So in valence bond theory, our hybrid orbitals, we looked at an atom, we smashed together the orbitals on that atom so they pointed in the right direction to make bonds. For MO theory, I'm going to take my two atoms, I'm going to bring them close together, and whichever orbitals overlap, I'm going to add those together. So what this means is that I'll be doing an s orbital with an s orbital. Px will overlap with px, py will overlap with py, pz will overlap with pz. When two atomic orbitals mix and form two molecular orbitals, one will have a lower energy, and we'll call that the bonding molecular orbital. and one will have a higher energy, and we'll call that the anti-bonding MO. The electrons, so each atom will bring in the valence electrons that it has available to it, plus, maybe some charges or maybe missing some electrons because of charges. And we'll make these molecular orbitals first, and then we'll fill the MOs. And the MOs fill with the same rules that we used to fill orbitals before. So alphabet principle, start at the bottom, move up. Hund's rule, so don't pair unless you have to. And then Pauli exclusion, if you have two electrons in an orbital, one has to be spin up, the other one has to be spin down. We can calculate a bond order from an MO diagram, and we will do this. There's a formula here. It's 1/2 of the number of bonding electrons minus the number of anti-bonding electrons. And a stable bond requires something greater than 0. In reality, if you get a negative bond order, you definitely did something wrong, because it's impossible to get a negative bond order if you've made your molecular orbitals correct. And the way that we think about this theory and look at it with molecules that we know is that you'll very often compare the bond order to a Lewis structure. So if you draw a Lewis structure of a molecule and it shows that there is a double bond in it, and you do an MO diagram of that same molecule and you calculate a bond order of 2, they're communicating the same thing. So you would say that the theories match. Now you might not get 2. They're different theories building up from different directions to explain what's going on in a molecule, so it's okay if the 2 give different answers. We always start with H2 because we only have that one orbital to worry about. So let's do MO theory for H2. So I have a hydrogen A and a hydrogen B. I'm going to bring them together, overlap these orbitals to make bonds. So the s orbitals on my hydrogen atoms, when I bring those atoms together, my 2 possibilities are that they are in phase or out of phase. If they're in phase, I get constructive interference where they overlap, which is just where they touch, They're not fully on top of each other because they're on adjacent atoms. So when the sides touch, that's my constructive overlap. My picture of my in-phase interaction would look like this big unshaded blob. This is a picture of my molecular orbital. It is the constructive interference one, so it is my bonding MO. It was a head-on or a pointed at each other, which I realize they're spheres, but s orbitals can only do sigma bonds. It's a sigma bonding MO. The way that we would label this is we would call it a sigma 1s. It has the head-on overlap and from 1s orbitals. If they interact out of phase, so one shaded, one not, my result is it's technically destructive interference. We show that where they completely cancel out by just putting a big line to be a node. And then, my orbitals, they look maybe just a little bit smaller in this picture. They shrink a little bit near where that node is. So this is still a sigma interaction. It's still 1s orbitals, but it was the higher energy, the out of phase. We call it anti-bonding, and we put a star. So we would call this a sigma star 1s, and it will have a higher energy. What this looks like when I fully officially put it together into an MO correlation diagram, which is an energy diagram, is something like this. So when I ask you for an MO correlation diagram, this is what I'm asking for. I'm asking for the energy scale and then these 3 columns of information that we have that make up the entire diagram. So on the outside, it's the atomic orbitals for the atoms that you're bringing together. So if HA on the left and HB on the right. Each one of those has a 1s orbital, and they're both hydrogens, so that 1s orbital is at the same energy for both of them. Each orbital also has one electron in it. Then those orbitals, the 1s on each, are going to interact with each other, and if they interfere constructively, I get this lower energy, sigma 1s. And so now this middle column, I have labeled the MOs for H2. The antibonding combination is higher in energy, and that's my sigma star 1s. And now when I'm looking at electrons in this, and you should list the electrons with the element and then also in the MO diagram, each hydrogen had one electron in its orbital, so my total that can go into the molecule is 2 electrons. Following Aufbau and Hund's rules, that is both electrons paired at the lowest energy level. Now, the bond order that I calculate from this, it's 1/2. It's the number of bonding electrons. So I've got my bonding MO here highlighted in orange. It has 2 electrons. My anti-bonding MO, highlighted in pink, has 0. So 1/2 of 2 is 1. It's a single bond. So my MO correlation diagram predicts a single bond. If I drew a Lewis structure, I would also see a single bond. So this actually works pretty great for H2. Or at the very least, I get the same answer. The next question I have here, just kind of going up to the next molecule, what about He2? And you will see questions written this way, like does this molecule exist? Or explain why this molecule doesn't exist. Let's try it out. So helium, this is my homonuclear diatomic molecule I'm going to look at. So I have heliums in the outer columns, so the left and the right, and I have helium-2 in the middle. So I've got my atomic orbitals on the outside, molecular orbitals in the middle. Each helium had a 1s orbital, and that 1s orbital had 2 electrons in it. So I've got my 1s for each helium. Those orbitals can interact constructively and give me a sigma 1s, or destructively and give me a sigma star 1s. The 4 electrons that I have, if I start filling up from the bottom, put in an electron, well, I don't have any other options of that energy, so I'll pair it up. And then I still have 2 electrons to fill in. Those are going to go into the antibonding molecular orbital. So there has to be a place to put the electrons. You just fill from the bottom energy to the top energy. You'll also notice that I do have dots, or kind of like a dashed line connecting my atomic orbital to the molecular orbital. Please make sure that you include these. So it doesn't seem like a big deal now, but it is going to help us keep track of which molecular orbitals came from which atomic orbitals. Okay, so this is my MO correlation diagram. If I calculate the bond order, I have 2 electrons in my bonding MO and 2 electrons in my anti-bonding MO. So the bond order is 0. There's no bond, and a bond order of 0 means we can conclude that He2 does not exist, which you would have predicted, right? It's a noble gas. Why is it going to bond to anything? It already has 2 electrons. It's very happy. And our MO diagram and bond order proves that. I am also going to draw pictures of the molecular orbitals here. So mostly to help you understand like why you won't have to draw as many pictures of orbitals for MO theory. So if I do pictures of the MOs, the lowest energy MO is a sigma 1s. It is the result of 1s orbitals coming into contact and constructively interfering. Then the other MO is a sigma star 1s. So 1s orbitals coming together and destructively interfering. So you'll notice these pictures look exactly like what we drew for H2. And it's because it's the same types of atomic orbitals. So if I ask you for pictures of the MOs, these sort of blobby cartoon pictures, that's what I mean. And also, I won't necessarily ask you in every single case because these pictures just depend on the type of atomic orbital that was used to make the molecular orbital. So a sigma 1s will look the same in every single molecule because it is the result of 1s orbitals coming together and constructively overlapping. Okay, so correlation diagram, bond order, picture of MOs. Those are the things that I'm going to ask you for. In MO theory, the components in the correlation diagram are the energy scale, the label for each of the three columns, the atomic orbitals with labels, the molecular orbitals with labels, the dots connecting the atomic orbitals to the molecular orbitals, electrons in the atomic orbitals, and electrons in the molecular orbitals. If I want bond order, I will ask for it separately. You'll probably get in the habit of doing it, but I will explicitly ask for it. And the pictures I will also explicitly ask for.